It says I'm live. All right. This is for you, Alethea. Because you asked nicely. Everyone say hi to Alethea.
Hi, Alethea.
All right. So yesterday we finished 22. And so 23, 24, and 25, I think should be pretty straightforward. But I just wanted to look at I don't know. So look at 26 and 27. They talk about a solid sphere and a hollow sphere. So you are given the I value. Let's just look at 26 first. You're given the I value. So the first thing to think about is that number, that constant, 2/5. So bigger or smaller than that of a solid disk. A little bit smaller, right? Because a solid disk is 1/2 mr squared, and this one's 2/5 mr squared. So, anyway, if you're wondering where that comes from, it comes from if you derive the formula using integrals in calculus, you end up with this 2/5 pops out for the solid sphere. And if you look down right below, the hollow sphere is 2/3. So a little bit larger. Does it make sense why the hollow sphere would be a larger constant than the solid sphere?
Yeah, because there's no masses close. There's less masses closer to the rotation.
Exactly. Yeah, exactly. Okay, so let's just answer 26, and then I think we'll do 26, maybe 28, 29, and then I want to try to get to 33 if we have time for it. That's my goal here in our short period. Okay, 26. So you have a solid sphere, radius is 50 centimeters, the mass is 40 kilograms. It's spinning at 2 rotations per second and experiences a torque of 12 Newton meters over a period of 6 seconds. That speeds up the sphere. Find the final rotational rate in rotations per second. So that's a lot of numbers, right?
Yeah.
Let's just go down number by number and identify what they're giving us. Okay. So, maybe before we do that, let's write out what's the big famous formula. It's not big; it's actually small. Torque. Torque tau equals I alpha. Right. Now, while we're at it, we might go, well, the way this problem is set up, they're giving us things like M, R. They're giving us rotations per second, right?
Yeah.
Which relates to what? Frequency, right? So they're giving us, they're telling us that the frequency started off at 2 rotations per second. So this is initially 2 hertz, right? They're giving us the torque. Well, so 2/5. Does this make sense what I'm talking about here? Like replacing I with the I formula for a solid sphere, replacing alpha with change in omega over t.
Yeah.
Because now, look at all of the symbols that we know.
We got them.
Do we know? I'm gonna be big brain here. I don't know if it's drastically different color. Oh man, the sun! Here comes the sun! Yay, Mr. Teletubby! What's tau for this problem? 12. Very good. 12 Newton meters. What's M for this problem?
40 kilograms.
40 kilograms. What's R on this problem? 0.5.
Wait.
What's T on this problem?
6.
6 seconds. So with all that information, we can find the change in omega.
True.
Right? So take our calculator. Grab a calculator if you don't have one already. So with our calculator, we're going to go, I'm going to multiply all this out. So I got 2/5 times 40 times 0.5 squared divided by 6. Well, you guys do that out and make sure you got the right answer. That's what I got.
What? That's not what I got. You got
Wait,
2.
I got point one.
I got 2.88.
Okay.
Oh, I know what I did.
We'll try this again. So I'm going to type in my calculator. I'm going to go 2/5 multiplied by 40 multiplied by the square of 0.5, then divided by 6. So then my second to last step, if you multiply that out, you get 2/3. So you get 12 equals 2/3 times omega, or change in omega, I should say. Sorry. Change in omega. And so the change in omega is 18. Now, there's a lot of mistakes you can make here because you might go, oh, I'm going to just add 18 onto 2. That's not correct, though. That's 18 radians per second. We got to convert that into a rotational rate. So how do you convert from omega to F? Divide by 2 pi. So if I go 18 divided by 2 pi, that'll give me a, what is that, 18? Don't forget on your calculator, when you divide by 2 pi, put that 2 pi in parentheses. You get about 2.86 revolutions per second. So what does that make our final answer?
That's what I got as my answer.
Huh?
That's what I got as my final answer.
Well, no, because our final answer is it started off at 2 hertz. It gained 2.86 hertz of rotational speed. So it's going to be 4.86 hertz is the final rotational rate.
Okay.
I hope this is visible. The sun is blasting the room right now, which is kind of nice. But it casts this big shadow. Well, I'm trying to see if I think it's all visible. I'm just wondering when that shadow comes down. Anyway, Alethea is the only person who'll ever see this video. I guess you can you can let me know if you can't see anything. Okay, so I hope the message there is clear. Like questions like 27, the next one is very similar to that. You just kind of have to identify what information you're being given. I would like to. I think you guys will figure out 28. It's one of those questions where you have different objects, and they tell you that, hey, all these objects are experiencing the same torque, right? They all have the same mass, the same radius. They're all experiencing the same amount of torque. So if we called the solid cylinder's acceleration just alpha, plain old alpha, what would the other objects' accelerations be in terms of alpha? So they're all going to be some multiple of alpha. Let's do a quick little power ranking here. Of those 4 objects described in number 28, assuming same mass, same radius, the same torque, who do you think would spin with who would have the biggest acceleration? Who would spin most easily?
The hollow cylinder.
The
Solid sphere.
It's the solid sphere.
Solid sphere.
Well,
Wait, why?
because torque equals I alpha, right? So do you agree that the bigger the I value, like for a constant torque, assuming the torque is kept the same? I think
Smaller I value.
yeah, the smaller the I value, the bigger the acceleration will be, right?
Mm-hmm.
Do you understand that? This might. That should fix it, I think. Everyone gets that?
Yeah.
Yep.
Yeah,
Is the I was smaller than acceleration?
Assuming that torque is constant.
Okay.
Does that all make sense? I hope that makes sense because that's the whole like key idea behind the I value. The I value, the bigger the I value, the harder it is to spin, right? Harder it is to accelerate. So if you have a smaller I value, you're going to spin more easily and have a bigger acceleration. So, anyway, I'll do one of them with you because I don't want you guys to not get the point of this. But so for this question, it says that the solid cylinder's acceleration is called alpha, just plain old alpha. So what you would do is you'd say, okay, they're all getting the same torque. Well, sort of the king formula here is this big formula: torque equals I alpha. So for the solid cylinder, SC for solid cylinder, torque equals I alpha, right? That makes sense? So I could write an expression maybe for this, which is that alpha is 2 tau over mr squared. We okay with that? Equal signs. Yeah?
Yeah.
So now I'm just going to do one with you. Which one do you want to do? You want to do the solid sphere? You want to do the hollow cylinder?
That one was solid. We should do, solid sphere.
Okay. By the way, can you guys just using some basic reasoning, can you tell us what, the hollow cylinder should just be what? It's a factor of 2, right? Because the hollow cylinder has double the I value.
Yeah.
So it should have half the alpha, yeah? Okay, so let's do one that's a little bit more complicated. How about the solid sphere? Solid sphere, okay? So for the solid sphere, I'd have same torque equals this time 2/5 times the same mass, the same radius squared, but this time it's the alpha of the solid sphere. You see what's going to happen next? Five tau over 2 mr squared. And so what you need to do here is go, well, wait a second. This expression for the solid sphere's alpha, it looks a lot like this expression for the hollow cylinder's alpha. There's just a difference of, instead of a 2, there's a 5/2. So the question is, basically,
Just flip.
well, I'll take a moment, see if we can figure it out. If I want to say that the solid sphere's alpha is some multiple, I'm basically asking 2 multiplied by what would give me 5/2. I'm asking 2 multiplied by what would give me 5/2. You see what I'm talking about?
Multiplied by.
5/4.
Yeah.
So does that agree with our common sense that the solid sphere ought to have a bigger alpha than the solid cylinder? Does it say that? Yes? How much more big, Lear? Huh? 5/4 times big leader. 25% larger? Yeah. So I guess you only have one left to do on your own there. All right. Will we have time to do? I think we do have time. Okay. So before we do the last one, I want to briefly talk about 29. So let's move forward. So 29 says you've got, just take a moment to read the question. This is all right. Do you all have a chance to read it? Yeah. Okay. So, firstly, do you understand that if this solid disk, let me make it solid. There we go. If you looked at 30, if you glanced at 30, you see that we're going to generalize this, or I'm going to leave this as an exercise for you, which I'll help you guys out if you get stuck, but I think you'll get it. If this disk was 1,000 kilograms, what kind of acceleration do you think we'd get when you release this block? Tiny, very good, very tiny, small. Yeah. Because it's not easy to rotate. I mean, 40 centimeters. I mean, this is a pretty big disk, right? The disk is like this big. So if that was 1,000 kilogram disk made of some really dense metal, it would be really difficult to get it to rotate, right? It would take a lot of force to get it to. Huh?
Like 1,000 kilogram block, maybe.
Yeah, it's like trying to push. You exert a force on 1,000 kilogram block. It's not going to accelerate very much. Conversely, let's say the disc was a lightweight wheel, like a bicycle wheel, and this was a heavy block. Then what would happen?
So that's just it's going to be ripping.
It's actually going to be a weird, probably like a chaotic kind of pendulum. But I'm saying just when you release it, if you measured that just for like a brief moment, right when you first release it, what would you think the acceleration would be close to? 9.8 meters per second. Right? Because if imagine the wheel's super lightweight and the block is super heavy, then it's going to be kind of like the wheel's not there, right? It's just going to, but like what Jager said, because of it's attached there, it's going to swing around and, we can make this, and I don't know, I'm kind of curious to see what it would look like. We can make it with maybe tomorrow. Okay, so anyway, we're going to solve this kind of like the Atwood machine problem. So you're going to say, well, what are the forces acting on this guy? There's tension. Huh? So there's tension, and there's also going to be 49 newtons pulling down, right? Make sense?
Yeah.
So I can write a formula for that. I can write, so I'm going to be using for this problem F net equals MA. And I'm also going to use torque equals I alpha. Guess what we're going to use that formula to talk about?
And alpha and angular acceleration.
Yeah. So we're going to use this formula to describe the block moving up and down, and simultaneously use this formula to talk about the wheel's rotation. Right? So let's write the formula for the block. Go ahead and do that.
Okay.
Okay. Okay. All right, check your answer. Hope we all wrote that down. Right? Yeah?
Yeah.
Okay. Now think about things from the wheel's perspective. You ask the wheel, yo, what's going on? He's going to say, well, I'm experiencing a force right there, right? A tangential force. How big is that vector? Nope.
No. It's
It was 49 before we released it.
oh yeah. It's
So imagine I'm holding the wheel, right? I'm holding the wheel. It's 49 newtons because of the tension's balanced. But once I release it, remember the Atwood machine? That tension is reduced.
yeah.
The answer is it's the same T, right? Because the tension exists throughout the string equally, right? So this guy, you guys remember the Atwood machine, right? The two
Yeah.
blocks on a
Yeah,
pulley.
yeah.
Okay. So the tension that's trying to pull this block up, we know the block's going to go down, but the tension that's exerting an upward force in the block is equal and opposite to the tension up here. So this guy's torque, so what's his torque then?
Well, it's F times R, right?
Yes, it's F times R. The force is T times 0.4. Very good. Do you all understand that?
Yeah.
So the torque on the wheel is the force multiplied by the radius.
Yeah.
The I value of the wheel is 1/2 m r squared. And now there's one last little trick here. What can I replace alpha with? Given that this equation,
Oh. Oh.
Would it,
There's.
could you just,
Angular acceleration over t? No, that's not.
let me ask you, let me back up a second. What letter do I wish was in this equation? Given that this equation has a T and an A. I'm really hoping this equation has a T and an A, right? Because two equations, two variables makes us happy because we can solve that. So what I have to ask myself is, can I replace alpha with an A somehow?
Yes.
49 minus over 5?
Well, remember this one? A equals alpha R.
There, yeah.
Oh.
That's what I was trying to go for.
That's a big important relationship, guys. So I'm going to replace alpha with A over R. You see?
I get you.
It feels me? All right. So it doesn't look like. Well,
We divide the 5.
we what?
Divide the 5, and then we have A equals. We just plug that in to the other.
Go ahead and just solve that, guys. I trust you guys to solve that. You don't need my help with that. I'll compare answers with you just so we can make sure, but. if you're stuck, that's the first thing I would do is I would solve this equation to get that.
It's 0.1 t per A.
What?
It's 0.1 times t per A.
The same thing, right? I could divide both sides by 10 and get 0.1 t equals A. That makes sense. I was just thinking that popped out to me. This is not the only way you can do it, right? It's solving a system. So that popped out to me, and then I could go, well, I could plug that in there and get 49 minus 10A equals 5A. So you get 3.26666. Okay, there we go. So now you're being asked, oh, don't forget, it also asks for the angular acceleration of the disk. So to get the angular acceleration, simply divide your A value by R. So it's pretty clear, right, how this question would lead into number 30. You're going to generalize this. Now, it's a different shape. It's a hollow disk this time.
Yeah.
So your I value is not 1/2 mr squared. It's just a regular mr squared, but the idea is the same. And so we don't have time to finish the very last question. I'll have to save that for, I guess, next week. But I do, before we end here, I want to talk about 31. You guys will, I think, be able to figure that out without too much trouble. I want to talk about 32, though.
What did you get for that angular loss?
You just divide that by 0.4.
Yeah, I got 8.
Sounds right to me. Oh, actually, we have time to very quickly discuss 31 and 32, I guess. So look at 31. It's a lot of words, but really, it's just saying, if you've got an Atwood machine, you know, saying Bob's got an Atwood machine and he's got all these different pulleys he wants to try out, right? Firstly, does it make intuitive sense to you guys that if you make an Atwood machine and you make the pulley a super heavy wheel, like a big, dense wheel, what's that going to do for the acceleration of the system? It's going to make it smaller, right? It's going to rotate more slowly, okay? So, like question A says, suppose pulley A and pulley B are both solid disks with the same radius, but pulley A has more mass, okay? Does that affect things? Pulley A having more mass, does that affect the acceleration? Yes. And then question B says you have pulley C and pulley D, same mass and radius, but pulley C is a solid disk. So pulley C is a solid disk, and pulley D is a hollow disk. Same mass and same radius. Which of these would allow the system to accelerate faster? Yeah. So this guy has a smaller I value. There's no calculation needed for these questions. It's just, well, this guy has a smaller I value, so therefore he'll rotate more readily, and he'll allow a bigger acceleration. Okay, so when you guys come back from your field trips and whatever, we'll discuss. This is a big idea here. The roly polies. We're gonna do a fun derivation. You think about that. Who would win a race down a ramp? Solid sphere, hollow sphere. So think about that. Some food for thought.